Chapter 3, Video Lecture. The information in this particular chapter is not found directly in the Wiley textbook, so you could consider this as an extra chapter. However, some of this information has been scattered within the Wiley textbook, and it does show up on the department exam. The title here says Energy, Chemical Reactions, and Cell Respiration. Nothing important about the first slide. This slide is of value to you. Energy is the capacity to do work. Sometimes they ask that on the department exam. So energy is the capacity to do work. Some people call it ability to do work. There are two forms of such energy. Potential energy, which is based upon stored energy, usually called energy of position. So if I have a pen raised above the table, my taking the pen from the table and raising it up in the air has provided with potential energy or stored energy, and some people call it energy of position. When I let go of the pen and the pen falls towards the table, that is called kinetic energy. And as you know, energy is simply going to go from one form to another. So you have potential energy being converted to kinetic. Kinetic energy can then be converted back to potential as I raise it back above the table again. Okay, I really don't care for this slide. This picture here, often found in several books, is to show you that you can raise the energy by creating more kinetic energy by moving ions from one place to another. So in the first picture on the left, I have intentionally created potential energy by moving all of the sodium ions to the outside and then allowing it to go through a channel that serves now as kinetic energy. So we created the potential energy by having sodiums in one place, and then it's going down a channel to create kinetic energy. Same is true for the atom. The atom has energy as it goes towards the core, and then you move it away from the core to provide it with more energy. So as the electron bounces from the higher energy down towards the nucleus, it releases energy. And that's what they're saying here. Same is true for the far picture. You're actually having more energy electrons at a higher state. As they go through all of these different chemicals in the between, they eventually end up in a low state. Sort of like what the water does. If you have a waterfall like the Niagara River, they're using the Niagara River as what? An energy source. So as the water goes down from high elevation down to low elevation, it goes through a turbine, and that turbine generates electricity called the hydroelectric dam, right? That's how it works. So next slide. Okay, now we have chemical energy. So that's one form of energy. That's what's in our food, right? So chemical energy found in our food, found in our body. Okay, next. Okay, remember we said this from last time. We said that triglycerides are the energy storage form in the form of a fat. So we mentioned that in the previous chapter. So triglycerides are the energy source through fat. Glucose, by way of glycogen, stored in the muscle. And then we also have ATP produced from glucose through the mitochondria. Then down here it says proteins. And we said that proteins play a very important role as a verb, as an action. Well, the only way you can have action is to have some energy to do it with. So proteins are very, very important as a chemical source to get things done. Remember, proteins are a verb. They are action, and they can only be done that way if there was enough chemical energy stored. Okay, the other forms of energy are electrical energy. That's what we're doing when we move ions across. So when we move ions across, that's going to be electrical energy. We're creating mechanical energy by muscles actually shortening. So when you actually contract your muscles, your contracting muscles is actually creating an energy of a mechanical action. Then we have sound energy, which is converting the vibrations of the sound of my voice, for example, through your eardrum. Okay? So these are all forms of energy to be aware of. Then the next one is radiant. That's your electromagnetic waves. That's how you're able to see the different colors of the rainbow, for example. Right? Roy G. Biv, you may have heard of that. Roy G. Biv, meaning Roy is red, orange, yellow, B. So it's Roy B. And that's blue. Then it's green, indigo, and violet. Okay. So the colors of the rainbow. Then we have heat. Heat is actually a form of random energy. That's how, if you're having molecules move around, and yes, it does play with role with temperature. Now keep in mind that heat, and this is what they ask on a test, heat is typically the wasted energy. So when you're exercising and you warm up, that warming up is actually a wasted form of energy. Okay? So heat is the #1 wasted form of energy. It does warm us up, but it's a wasted form of energy. Here's your Roy G. Biv. So red, orange, yellow, green, indigo, blue, and violet. Okay, next slide. Don't care too much for this one. Okay, the 3 laws of thermodynamics, make sure you know them for a test. They're likely to be asked. So the first law of thermodynamics, says energy is not created nor destroyed. It only simply changes form. Okay, so it simply changes form. Then the second law of thermodynamics says that energy is transformed. Some heat energy is always lost as heat, and that's what I mentioned a moment ago. Okay. Right, so that was the first law and the second law. Okay, don't care for that one. Okay. Let me make sure I got them all covered first. Okay, so we're cool on that. I'm good with that. Okay. Okay. So far so good. Okay, then we have our chemical reactions or chemical equations. This is a pet peeve I have. Okay, here's my pet peeve. You have to understand that what you start with is called reactant. So what you start with is called a reactant. What you end up with is called a product. So the chemical reaction or the chemical equation always goes from reactants converted to products. And if it takes a whole lot of energy to go from reactants to products, it's less likely to happen. If it takes less energy to go from reactants to products, then it's more likely to happen. Okay, so here's how the chemical reaction is written. A plus B to make C. So A and B are your reactants, and C is your product. Okay, that's how it works. Okay, these are the 3 main kinds of reactions down here at the bottom. We have the decomposition, which is basically breaking things down, where we have A, B put together. So A, B is put together, and then it is split apart into A plus B. That would be a decomposition, where A, B together is now split into A separate and B separate. Then the next one here we have on the screen is synthesis. That's just the opposite, when you have A separate, B separate, joined together to make AB. And then the last one is exchange, where A and B on one side make something new, C and D on the opposite side, which also has a chance to go from C and D back to A and B. Okay. Sometimes the reactions are reversible, sometimes they are not. This is an example of decomposition. So this is what I said, A, B together, split up into A separate, B separate. Okay. And hydrolysis is the one we learned in the other chapters before. So that would be a good example, hydrolysis, where we're taking AB and splitting it into A plus B. Then we have synthesis, where A and B are joined together to make AB. We saw that last time too with dehydration, where dehydration meant that water was removed to join two things together. So we saw that last time as well. And this is the exchange one, where AB plus C breaks down to A plus BC. They simply change places. You will not see too much of this. Okay, don't care for that. Don't care for that. Don't care too much for that. I do care for this. Now, earlier I said reactants versus products. If it does not take too much energy, notice it says energy is released. This gets hot. So usually this is something that is releasing far more energy. And if it releases far more energy, exergonic means it's going to get hot. Then endergonic over here is where reactants are less likely to turn into products because it takes a lot more energy to be supplied. That means it has to go in. So it's less likely. So this is usually going to be colder. So exergonic is going to release heat. So exergonic will release heat. Endergonic means more heat has to go in, so it's actually going to be colder. Okay, next. Okay, ATP cycling. I don't care about this slide per se. Okay, I really don't care for that slide either. We talked about the high energy phosphate group in the other chapter, where I said that the mitochondria produces ATP, and it's the last energy. See how it has a little squiggly line? That's a high energy bond. By my releasing this phosphate group and attaching it to something, I'm going to provide that thing that I've attached to with energy. And that's called phosphorylation. So by removing this phosphate and attaching it to something, it then gives it energy. Well, that's phosphorylation. I don't care for that slide. Here's a reversible. Don't care too much for that. This is a nice summary sheet. You may want to use this. That's why I'm giving it to you as a video. So this is a nice summary to be aware of. So if I'm not going and I say I don't care, I don't care, I don't care, usually when I skip a lot of slides, it's an indication that there's a better picture coming up like this one here as a nice summary. Okay, now I do care for this term called reactivation energy. Let me give you my definition for this term. Activation energy is the energy it takes to go from reactants to products. Some people say, is that the energy it takes for a reaction to happen? Yes. So activation energy is the energy it takes for a reaction to happen. If you somehow were able to lower the activation energy, that means less energy is needed and more likely the reactants will turn into products. Now, what substance actually lowers activation energy, meaning that it takes now less energy for reactants to turn into products, and that substance would be an enzyme, and that's mentioned at the very bottom of this slide. So enzymes are designed to lower the activation energy. Okay? So that's why I'm going over this particular chapter, not found in the previous chapter of your official book. So enzymes are designed to lower the activation energy, making it more likely that reactants will turn into products. Next slide. Okay, speaking of enzymes, that's what I'm headed towards. So these are now referring to enzymes. Now, enzymes do reduce the activation energy. That's something we just said. So enzymes lower the activation energy. They make other physical things happen more quickly. So your chemical processes actually go faster by reducing the activation energy. Okay? They only facilitate in the reactions that would already occur. So they don't make things happen, they just make things more efficiently happen. That's what I'm getting at with enzymes. They just make things more likely to happen. And notice it says here, increases the rate of production formation. It makes reactants more readily turn into products. It just makes it more efficient for reactants to turn into products by lowering the activation energy, the energy it takes for that reaction to occur. If I told you I want 10 chapters done by tomorrow, test tomorrow, well, you know that's not going to happen because that's just too much. But if I said, okay, let's break down the 10 chapters into 2 chapters each per test, then you know that that's more likely to happen, right? That's exactly what this is like. It's taking smaller chunks but getting them more efficiently done. Now this picture is a classic. And I don't know why they said lovers here. I'm pretty sure they meant lowers. Big old typo there. Now this picture is almost in every textbook, and again, like I said, it's not in your Wiley's official textbook, but it should be because this is often asked on any test. So first thing you notice is presence of the enzyme lowers the required activation energy. So let's look at the chart. The red line represents what would happen if I did not have the enzyme. That's a bigger, steeper hill for me to climb. That's the red line because I don't have the enzyme. But with the enzyme is the blue line. See how much lower that hill is. So with the enzyme, it's more likely to occur because it lowers the amount of energy it takes to make it happen. Okay? And here I have reactants turning into products. Okay, so it does help with the lowering of the activation energy. Okay, next slide. Don't care. Okay, this slide I do care. Now these are going to be the features of an enzyme. This part would normally have been in the previous chapter. It should have been in most books, but I want to make sure it's covered. So these are the features. The first feature is that enzymes have a very specific active site. See how this substrate fits perfectly into that active site. It is very specific. So enzymes are specific to their substrate. So enzymes are specific to their substrate. They have a specific active site. So you cannot have a different key for a different lock. That's what I'm getting at. You cannot have a different key for a different lock. The lock and key have to match. Now let's take an example before I go any further. We have something called lactase. That's an enzyme that you find to help break down your milk. Lactase works on a milk sugar called lactose. Now Asians, and this is typically Asians, they have a problem where they don't make enough of this lactase. That's what's called lactose intolerance. Since they don't have the lactase, they really can't break down a lot of the lactose, leading to upset stomach, diarrhea, bloating, gas, things like that. Okay? So you have to have a specific enzyme for a specific substrate. So a specific lactase for a specific lactose. Okay. And this is the example I just provided you with. So this one was one, lactase going with lactose. That's the example I provided. Don't care for the others. Okay, these are more features. We've already taken care of number one. So I already told you enzymes have a specific active site. Okay, enzymes have stresses chemical bonds. Okay, products are released and enzymes may repeat. So enzymes are not used up in the reaction. So enzymes are not used up in the reaction. And that means that the process can continue over and over. It also means very little of the enzyme is needed to work out a lot of the reactants and the products. So very little enzyme is needed to work on a big batch of products and reactants kind of thing. So this picture says it best. Here's my enzyme, lactase. There's my milk sugar called lactose. There it is together. Then the enzyme breaks it, shown right here, broken. Of course, it does it through the process of breaking the bonds, which would be the hydrolysis. So hydrolysis did play a role in here. Not shown, but hydrolysis played a role. Then we broke them up, and now it's free to do it all over again. So that's why I said that enzymes are not used up in the reaction. So here's another example, same thing. Okay. Cofactors are your coenzymes. So vitamins serve as coenzymes. Just be aware of that if someone asks you. That'd be a one-liner if anyone ever cared to ask that. So vitamins are a good example of coenzymes. Okay. Don't care for this slide at all. Don't care. Okay, this one I do care. When it comes to naming enzymes, not always, but most often, enzymes end with ASE. So not always, but most often they end with ASE. So lactase is one I gave an example of. Okay. These are all the things that play a role. So we said that enzymes are not used up in the reaction. Enzymes lower the activation energy. Enzymes have an active, specific binding site. So these are the things we've said so far. And then here again, it actually does what? Increases the rate of the chemical reaction. So enzymes will increase the rate of the chemical reaction. Okay, don't care. Okay, we also said this before. Because enzymes belong to the protein category, we've said that enzymes can be denatured. How? Enzymes, because they're proteins, can be denatured by temperature, which is heat, and the other one was change in the pH. And we mentioned that before. We're now connecting it. So here's what we have so far. Enzymes increase the reaction rate. Enzymes are not used up in the reaction. Enzymes have a specific binding site. They're specific to the enzyme, that kind of thing. Okay, so here's an enzyme being denatured because of higher temperature. We've also said already pH, so here's a slide just for that as a separate one. So yes, and this is the example I gave earlier, where in the mouth we have an enzyme that works at pH 6. By the time it gets to the stomach, which has a pH of 2, the enzyme stops working because it gets to a different change in the pH. Because you denature the enzyme changes shape, and if it changes shape, it loses its function because it's now different. Remember the rule. Changing the structure can change the function. And when you denature a protein, you denature an enzyme, you're basically changing the shape of it, which changes the function of it. So you can see that there are certain themes that I've been bringing along all the way. Well, as we go from chapter to chapter, that's what's going to happen, these major themes. Same is true for A&P 2. There are major themes along the way, and this is one of them for here. Don't care. Okay, this one I do care for. I'm only going to go over the picture. I don't care about the wording on the side. So here I have an enzyme. Here's the active site that we've spoken of. And here's the substrate. So far, no big deal. This is what we saw in the other pictures. But sometimes we have this storyline. So I just changed slides. So if you haven't noticed, I was in this slide here. Now I have this slide. This is going to be a problem. This is called a competitive inhibitor. The problem is it's like musical chairs. This is some chemical that came in here and now will not allow the substrate to stick. That means that the enzyme can't do its job. This would be an example of, say, a poison. And there are poisons out there, big chunks of poisons out there. Those poisons are designed to block, and that's why they call it inhibit. They block the substrate from reacting with the enzyme. This can mean a life and death situation, because now a reaction that's going to take only thousandths of a second, milliseconds, now this reaction may take years. And that's no exaggeration. That can actually happen. Okay? That can actually happen, where something that takes only seconds to happen without the enzyme working may take years to happen. And that's a problem. Okay? So there are poisons out there that are designed to make things like that happen. Okay? So that's called a competitive inhibitor. Okay? And I don't care for that slide. Yeah, make sure you know this one, though, the one I just went over. So make sure you're comfortable with this one, where you have a blocker, sort of like musical chairs, and that guy can't sit anymore. That means that enzyme cannot break down that substrate. And what would normally take only seconds or milliseconds to do will now take years or never. Okay, very, very important. Okay, don't care for any of these slides I'm now skipping. Okay, don't care for this either. Okay, there's my magic word, phosphorylation. You already know it. I don't care for the rest of this, but I already told you phosphorylation is the act of putting a phosphate group on something to provide it with energy. Look what it says down here. Phosphorylation, and then down here it says turns on some enzymes. There you go. Okay, so phosphorylation provides enzymes with the energy to do something. Matter of fact, you'll see later on, phosphorylation provides many things with the energy to make happen. Okay? So phosphorylation is the act of taking a phosphate group off of ATP and attaching it to something and providing it with energy. Okay. All right, here's a clinical example. I often like to stop at clinical boxes. I haven't thus far in the other chapters because it wasn't as important, but this one is. Drugs increase or decrease based upon the enzyme activity. So look what it says here for this one, penicillin. Penicillin targets a bacterial enzyme, slowing the spread of infection. Okay. So this one is actually blocking a bacterial enzyme, which helps us by not having that infection spread. Okay. So you can see that, yeah, enzyme inhibitors can play a big role. Okay. Next. Lactose intolerance I've already discussed, so you can read it if you want to. It's the same thing I said earlier about the lactase enzyme and the lactose issue. So it's mentioned here. Okay, now I'm on a topic called cell respiration. So cell respiration. I have dedicated a separate supplement video just for that. So there's a separate supplement video on cell respiration. Please look at that. It's going to be under Chapter 3, Supplement. And you'll see one titled Cell Respiration.